Alright, so we're going to continue on our talk on circuits. And to begin with, let's talk about parallel circuits. So we talked about series circuits in the previous class. Now the another circuit arrangement that is possible is of course a parallel arrangement. Just like we used to have parallel connections in capacitors, we can have parallel connections of resistors. So this is an example. Sorry about that, I realize I don't share my screen yet. Right. Alright, so here's my screen. And so this is an arrangement of a couple of resistors arranged in parallel connections. So in parallel connection, what happens is the current divides out. So you can see clearly I comes in to this junction, and then I gets divided into two branches. Wherever the current can flow, it will flow. So since you have two paths to go, through R1 or through R2, current will take both of them. So therefore the total current comes in, gets divided out into two branches, so the current is not the same through R1 and R2 anymore. In series circuit, the current was the same. What is same in this case is that the potential difference between the two ends of both R1 and R2 is V. Right? So the voltage drop, if you connect a voltmeter, it will read the same reading for R2 as well as R1. Right? So the potential difference for both resistors are the same. The current divides out, so the total current is equal to the branch currents I1 and I2, and I can be given by Ohm's law. So whenever I don't mention anything about Ohm's law not being valid, consider all resistors to be ideal. Right? So therefore Ohm's law is always valid unless otherwise specified. So you have I, that is the total current, equal to the first branch current I1 plus the second branch current I2, and each one would be V1 by R1 plus V2 by R2, but V1 and V2 are equal because they are connected in parallel. So in both cases you have V, and you can take V out and write the expression as V times 1 over R1 plus 1 over R2. If you remember your circuits, then from earlier studies, you recognize this 1 over R1 plus 1 over R2. This kind of a combination is how we combine resistors in parallel. So I can write 1 over R1 plus 1 over R2 as just 1 over R parallel, RP. So 1 over RP is nothing but the two combinations, 1 over R1 plus 1 over R2. So this gives me the equivalent resistance in parallel. Alright? So 1 over R parallel, 1 over R equivalent in parallel is nothing but 1 over R1 plus 1 over R2, but not only 1 over R1 plus 1 over R2, but also any other resistors you connect in parallel, this formula works. So thus, R1 and R2 can be combined into one single resistance. We call that resistance R of P, and R of P in general is basically this summation here. 1 over R equals all of the summations. But remember always at the end to flip over, just to inverse all of these relations, because ultimately you would require R and not 1 over R. Right? So let's do an example. And also remember that in parallel, the currents are all different. Unless, of course, you have the same value for each resistor. Then the current is equally shared. Alright, so let's do a problem. A 3 ohm, a 6 ohm, and a 9 ohm resistor are placed in parallel and connected to a 12 volt battery. So what is the total current flowing through the system? Well, first you draw the circuit. They're connected in parallel, so this is a parallel arrangement of the three resistors. They're connected to a battery of 12 volts. So the current basically produced by the battery goes out of the positive terminal, and then it sees three junctions or 3 points that it can divide into. So first you meet this junction, so the current gets divided. Let's say I1 goes through R1, and that the rest of the current goes through this wire. Then it sees another junction, so the current again divides out. Let's say I2 goes through here, and then what's left over is I3 that passes through R3. So I want not the branch currents, I want the total current I. So what I can do for very easily is I can combine all these different resistors into a single parallel resistor. Then I can find the current through it. The current through that parallel resistor would be the current in the whole circuit, the total current. So therefore, the first thing I do is I use my relationship for 1 over R equivalent for the parallel connection. So you have 1 over 3 plus 1 over 6 plus 1 over 9 omega to the power minus 1, because remember it's 1 over R. and you get 11 over 18 omega to the minus 1. But ultimately you need R, so you have to invert 11 over 18 and you get 18 over 11. So you get 1.6 ohms. Now take a moment and think about this number that you got. You have R1, R2 and R3. Imagine if they're connected in series, what would you have gotten? You have gotten 3 plus 6 plus 9. That would be in series. So therefore the total resistance in series would always be greater than each individual resistance because they're just adding up. But since you have connected the resistors in parallel, you see the equivalent resistance is smaller than even the smallest resistance, 3 ohm. So therefore if you connect resistors in parallel, you're ultimately decreasing the overall resistance in the circuit. Alright? So therefore if you have a smaller resistance, this is the one equivalent resistance, you now have a new circuit which looks much simpler, and the current through that equivalent resistor would be the total current in the circuit, and that can be just found by Ohm's law. V equals IR, so I is V over R, so you have 12 over 1.6, that is 7.3. If you remember from last class, we did the same resistors for series connection. The current was about 0.7 amperes or so. Here you can see the current has greatly increased. It's now as much as 7 times more than in series connection. And why is that logical? Because you see the total resistance in a parallel circuit is smaller than the total resistance in a series circuit. Alright, so the current is bigger in a parallel circuit. So if you want your circuit to produce the biggest amount of current, then you would always add your loads, your bulbs or your lamps or your hair dryers, whatever you want to connect, you would always add them in parallel if you want a large current passing through them. Alright. Okay. So what if now I want the individual currents, the current in each resistor for the same combination? Now I know the total current, so the total current is 7.3 amperes, right? So I1, I2 and I3 must be equal to the total current. Cannot be more, cannot be less, because charge is conserved, right? So if charge moving, that is current, is 7.3 coming out of the battery, then all of that must be shared by each of the resistors put together. All right. So now I can find the individual currents again by an application of Ohm's law, because I know the current is different. I1 and I2 and I3 will have different values, but the voltage across R1, R2 and R3 would be the same. So therefore I can easily apply Ohm's law. V equals IR. So I1 would be just V1 over R1. V1 is 12, R1 is 3, so you have 4 amperes. I2 would be V2 over R2, but V2 is also 12 divided by 6, you get 2 amperes. And then I3 would be V3 over R3, which is again 12 over 9, which is 1.3 amperes. The total current, of course, is 4 plus 2, 6 plus 1.3, which is 7.3 amperes. The total current cannot exceed I. The total I1 plus I2 plus I3 must be equal to the total current that is generated by the battery. Alright. Okay, so also look at these numbers and think about them a little bit. The smallest resistance draws the larger current, and that makes sense, right? Current will flow most easily through the resistor with the smallest resistance. So the resistor with the smallest resistance will draw or will take up most of the current. Alright. So if you have questions, please feel free to unmute yourself and ask. But alright, so yeah. No. Who is Mayub Ali? I don't know you. Oh, okay. Alright, so yeah, there is your discussion question. So the numbers are starting from 4 because we did 3 before in the previous class. So take some time, think about it, and then you can respond in the Google form. Don't submit the Google form. I'm giving you 1 minute to answer this. No, 4. The forms are also 4, 5 and 6. 4, 5, 6 and 7. So yeah, you have 1 minute to select, and then we are going to move on to the next slide. And don't submit yet because you have, I think, let's see, 1, 2, 4 questions in the same form. So don't submit. Right, last 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Alright, so moving on. Another discussion question we have: a 100-watt light bulb is placed in series with a 60-watt light bulb. Given that the brightness is proportional to the power dissipated, which will burn brighter? Is it A, B, C, or D? Again, you got 1 minute to make your choice. Right, so last 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Okay, moving on, we have another discussion question. Again, you get 1 minute to think about it and then make your choice. Right, last 10 seconds. 1 minute na quite second dite pare. Also, you don't have to submit, so you can answer even after this. Nay, if E isn't there, probably E is not the answer. So yeah, if any of the options are not there, then that is not an answer. Alright, last 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Alright, moving on. Let's talk about something probably you have met in your previous classes with engineering courses: Kirchhoff's laws or Kirchhoff's rules. So Kirchhoff was an experimenter, and he worked a lot with currents, and suffice to say he had a lot of contribution in the field of currents and electricity. So he devised two rules to analyze circuits. One rule is known as the junction rule, right? So that is commonly also called Kirchhoff's current law, KCL. So this junction rule tells me that the summation of the currents that is going into a junction equals to the summation of currents that are coming out of the junction. All right, so this is coming out from the conservation of charge. So charge cannot stop or accumulate in any one point in a circuit, if of course you don't have a capacitor. Then charge, whatever charge goes into a point must also come out. So therefore, let's say you have two currents going in, then the current coming out, or the summation of the currents coming out, must be equal. So if I1 and I2 goes in, so I1 plus I2 is the current into the junction, then I2 plus I3 plus I4 is the current out of the junction, let's say, and I1 and I2 must be equal to I3 plus I4 plus I5. That is basically what that means. All right. Then there's the loop rule. The loop rule is also commonly known as the Kirchhoff's voltage law, or KVL, and this is concerning the conservation of energy. So if you go around a circuit, basically you meet a battery. A battery supplies potential energy per unit charge, or the electric potential, or the EMF. So any load that you connect, or any resistor that you connect, will basically get a share of that energy. All right, will basically get a portion of the energy per unit charge that is supplied by the battery. However many resistors you connect, doesn't matter how many. In a closed loop just means you start at some point, you walk around the whole circuit, and you end up at that same point again. There is no holes, you just go from one point back to the same point again. That's a loop. Around that loop, any resistor you connect will draw some portion of the energy from the battery, and you have to add up all of the voltages dropped, or the potential drawn by each of the resistors, and they must all add up to give you 0. All right, so that means the battery supplies some energy, the resistors take away some energy, so the positives and negatives must all sum to 0. So I think it's better to do it with an example. So I'm going to show you an example. All right, so first let's forget the numbers for a bit, and then just focus on R1, R2 and R3, and V1 and V2. So I'm going to just focus on the letters, doing some algebra right now, not the numbers. So you can forget about the numbers for a bit. All right, so first thing you do in circuit analysis like this, because you see that there are two batteries and some resistors, it's not quite obvious if the resistors are connected in series or parallel. It may look parallel, but you can't take that for granted because it's not that simple of a circuit. But we can see one thing for sure: there are at least two loops that we can define, two closed loops. One loop may be this one right here. So this loop is one loop. So let's call that loop 1. And another loop that we can define is this one, right? The upper loop. You can of course define another loop, that is the one big loop, one outer loop, but I just want to stick to these two. In the slide, which I will upload after the lecture, the problem is done in a slightly different way to the one I'm showing you now, so that you have two kinds of methods to follow. Whichever one you like, you choose that one. Or if you did some other method in engineering class which you like better, take that as well. I don't mind, as long as your work is consistent and your work makes sense, it's all fine. All right, so now let's see what we are going to do. So first thing that you do is you pick a junction that you want to look at, and then you basically define all the currents in that junction. So for me, I think you can pick any junction, okay? So for me, I think the good junction that looks like I can use is this one. So junction is any point in the circuit where basically a current can divide out, right? Branch out. So for me, I'm taking this to be my junction. All right. And so let me clear this loop thing. just because we know what we're dealing with. Alright, so now let's get back to it. So this is the junction that I have defined. I've chosen it. You can choose any other junction, that doesn't matter, as long as your work is consistent. Alright, so now you define your current. So current is usually defined as a flow of positive charge from the positive terminal of battery into the negative terminal, right? So therefore, let's consider this branch first and define R2, I2, because it's just easy. So you see this is V1, and V1 will generate a current that will go through R2. Usually you don't have, like, this is completely arbitrary. I'm picking a direction just out of good faith that the positive charge will flow out of the positive terminal of the battery and generate the current in that direction. So what I'm saying is I'm choosing this direction to be the current through R2. So let me call that I2. So I2 is going into the junction. All right. What else? So I see in the lower branch, I see that there is another battery, V2, that is again going to generate some current, and I'm sticking to my convention that current is coming out of the positive terminal and going into the negative terminal. So therefore again, I'm defining a current in this direction, and that I'm calling I3. Okay. So I1 goes into the junction, I3 also follows this wire and goes into that same junction. So I1 and I2 goes in. So you can have I1, that is the leftover current that will pass through R1 to go out of the junction, or you can have it going in. It doesn't matter the direction at the end, because ultimately you will see the answer works out if you do your algebra right. So for me, just for fun, I'm going to say that current I1 goes through here, goes through R1 like this. So therefore I1 is actually exiting the junction, right? I1 is going out of the junction. So I2 and I3 goes in, I1 leaves the junction. So firstly, the junction rule of Kirchhoff tells me that the current, the summation of current going into a junction is equal to the summation of the current going out of that junction, right? So what is I in? The currents that are going in are I2 and I3. So I can write I2 plus I3, and what is the current going out? Well, I1 is going out, so I can write that equal to I1. So that is equation 1. Okay, so that's from the loop rule, from the junction rule, that I'm getting one of my equations straight away. Alright, now comes a little bit harder part, that is the loop rule. So let us define two loops that we have already defined. One is the lower loop, the other is the upper loop. And basically you choose a starting point. Alright, you can choose any point, just pick one. So I am picking this to be my starting point. So a closed loop would be I walk around this whole loop, loop 1, and then come back to that X again. Alright, so I walk this way. I start at this green cross and I go this way, and then come back again, back to the same X. So that is loop 1. Alright, so here you will walk through each of the circuit components, and you have to be careful about the sign convention. So what is the sign convention? Alright, so I start walking, right? Let's imagine that I'm walking with a positive charge in my pocket, right? So I'm starting to walk from this X, and I first meet the negative terminal of the battery. And I want to climb this hill and go to the positive terminal. So that means, remember what the electric field was? The electric field is always from positive towards negative. So to make this journey with this positive charge in my pocket, I have to say climb a little hill, right? I have to go uphill from negative terminal to positive terminal, opposing the electric field. So that means what? My potential energy should go up, right? It's like that gravitational analogy again. So therefore, since my potential goes up, it should be a positive sign. So therefore, I get a positive V2 in loop 1. Right? So positive V2 for this uphill climb. And then I meet the resistor. The resistor basically apart from the battery, every other place, every other component in a circuit will have electric field and current in the same direction. So therefore, the current I3 I have defined to go this way, right, from right to left. So I am also moving in the same direction as the current. Through a resistor, if I am moving with the same direction as the current, then I'm moving with the electric field. If I'm moving with the electric field, I don't have to do much really. I can just sit there and the electric field will take me for a ride because I have a positive charge in my pocket. So therefore, I get lazy and my potential energy goes down. Right? So therefore, I lose potential energy, or I lose electric potential if I go through a resistor. So therefore, I end up with a negative sign in front of my potential drop across R3. Now, what is the potential drop across R3? By Ohm's law, it is I3 times R3. So minus I3 times R3. Okay. Now what else? So I go through R3, then I go through this wire. The wire has no resistance at all, so I just go to the junction, and then I turn this way. I'm now going in this direction through R2. So I'm going through R2. What is the current through R2? The current is I2, right? That is the current that I have said goes through R2. So therefore, since I'm going against the current, that means I'm going against the electric field through a resistor. So I have to push my way through the current. That means I have to increase my potential energy. I have to do some more work. That means I will increase my electric potential. So therefore, I get a positive charge. So through a resistor, if you're moving against the current, you get a positive charge. If you're moving with the current, you get a negative charge. So therefore, I have a plus I2, that is the current through R2 times R2. That is the potential drop across the resistor R2. And then I pass through R2 successfully. I've done enough work. And then I meet another battery, V1. But here I meet first the positive terminal of the battery. So this is like a kind of a downhill drive because I'm going in the same direction as the electric field. Electric field, remember, is from positive to negative. So I have a positive charge in my pocket, so I don't really need to do much again. To go in the direction of the field, I can just sit there and the electric field will take me for a ride. So therefore, I can basically just slide downhill. So my potential energy, or the electric potential really, goes down. So therefore, when moving from the positive terminal to the negative terminal of a battery, I end up with a negative sign. So negative V1, because my energy, I'm losing energy as I'm doing it. I'm not doing any real work at this point. I'm not doing much work. So therefore, this is minus V1. So then I end up here. There's nothing, no resistance, and I can just go straight down the wire back to X again. There is no resistance. So I've completed my loop. And Kirchhoff says that all of these must sum up to 0. Okay? So let's rearrange this a little bit to make it look nice. We make the currents in the same direction. So I have I2 R2 minus I3 R3. That is equal to V1 minus V2. Okay? Alright? So that is equation. Alright, at this point, if anyone has questions, please let me know. Yes? R3, yes, R3. Yes. Because you're flowing with the current, you're not doing real like any extra work. So basically your energy goes down. Yes, because you're pushing your way against the current. Alright. So then let's go to loop 2. Loop 2 is the upper loop. Okay. So I start, let's say from here, I go around the loop, let's say in this direction, and I complete my loop just like I did for loop 1. Alright, so now this is my journey, the blue pen. So I start my journey here. I start walking again with a positive charge in my pocket, as always. you must have extra positive charges lying around in your bedroom so that you can always pick it up. And then again, I first meet the negative terminal of the battery, right? And then I have to go to the positive terminal. That means I am going against the field. Negative to positive is against the field. So again, I have an uphill battle to climb. So I'm going uphill, so that means my potential goes up, so I have a positive sign. So I have a positive V1. Alright? And then I meet a resistor. Again, resistor current is this way, I2. I am going with the current, so I have a negative sign. So I2 R2. Then I go to the wire, no resistance at all, no potential drops. And then I meet R1, the resistance R1. Again, I1 is this way, I am also moving this way, so I get a negative sign again. So I1 R1. Then I go through the wire, back down to the wire, back down to the junction where I started my journey. So I meet no other resistance, so therefore this sums up to 0. So let's clean this up a little bit. I have I1 R1 plus I2 R2, that is equal to V1. So that is my third equation. So what is my goal here? My goal is to find all of the currents. Alright, I want to find all of the currents in each of the resistors. That's my goal. Okay, that's fine. So I can use my equation. So there are 3 currents and there are 3 equations. I can solve them. I look at my loop equations 2 and 3. I see that I have in equation 2 I2 and I3, but in equation 3 I have I1 and I2. So I2 is common, so I can keep I2, but I1 or I3 I have to choose and let something go. Which one do I let go? Well, I1 I have an equation, so I can basically replace wherever I see I1 by I2 plus I3. So I1 gets replaced by I2 plus I3 times R1 plus I2 R2, that is equal to V1. So let's clean this up a little bit. I2 is multiplied by R1 but also multiplied by R2, so plus R2 plus I3 R1 equal to V1. So that is actually now my equation 3, my modified equation 3. So I don't need this anymore. Alright, so now let's use your numbers. You like numbers, so I'm giving you numbers. Well, what happens to equation 1? Well, equation 1 with the numbers, why can't I select my pen? Right, so equation 1 with the numbers look like this. Equation 1 becomes I2 I don't know, but I know R2, which is 6 times I2 minus R3 is 3, so 3 times I3 equal to V1 minus V2, which is 12 minus 3, which is 9. I can write that simply as dividing by 3. This is 2I2 minus I3 equal to 3. So that is one equation. Let's call that equation 4 or something. And then equation, sorry, this was equation 2, not 1. All right. So now the equation 3 from loop 2, what does that become? Well, with the numbers, equation 3 becomes I2 I don't know, R1 is 6, R2 is 6, so we have 12 I2 plus R1 is 6, so we have 6 I3, and that is equal to V1. So V1 is 12. So I can divide this by 6 and I get 2 I2 plus I3, that is equal to 2. So this is equation 5. Now I can solve these two equations. They have both I2 and I3, so simultaneously it is very easy to solve. So you have 2 I2 plus I3 equal to 2, and to that you can just add your fourth equation, which is 2 I2 minus I3 equal to 3. So if you add them together, I3s happily cancel out, plus and minus, you end up with 4 I2 that is equal to 5. So I2 is nothing but 5 over 4 amperes. So that is the current through R2. Okay, so then I have one of the currents, so I can very easily find the other current using, let's say, equation 5. So equation 5 now tells me that I3 is 2 minus 2 times I2, so 2 times 5 over 4. So 2, this is 5 over 2, so 2 minus 5 over 2 is 4 minus 5 divided by 2, which is minus 1/2 ampere. So this is interesting. Why is there a minus sign? So minus sign tells me that whatever direction I have chosen for I3, this from left to right, is not actually the correct one. The correct one would be from left to right. Okay, so not from right to left. So that is what that minus sign indicates. So the minus sign just tells me that my assumption of the current was wrong, but it doesn't matter because your answer tells you that accurate answer anyway. So whatever direction you choose doesn't really matter at the end of the day if you have done your work correctly. All right, now I still have one more current remaining, that is I1, but equation 1 tells me that I1 is equal to I2 plus I3. So I2 is 5 over 4 plus I3, meaning minus 1/2. So what is that? Well, we have 4 here, so 5 minus 2 is 3 over 4 amperes. So that is again a plus sign, so that means I have chosen the directions for I2 and I1 correctly. I just chose the inverse direction for I3. So it would be I3 going out of the junction because it's a negative sign. I2 would still be coming in, I1 would still be going out. So I2 comes in, I1 goes out, and I3 also goes out. Alright, so that would be the actual current measurements. Alright, so you have now found all the currents, so that was my first goal. Then you can pick any one of the currents and find the power in each of the resistors, because P is equal to I square R. So if you want the power through the 3 ohm resistor, you just multiply the current to through the 3 ohm, which is I3, square it, I square times R. That would give you the power. Alright, so again, questions? Any questions regarding what we have worked out so far? Alright, so just to let you know, alright, good. Just to let you know, in the slide, I have considered the bigger outer loop, so that would be a different work, but you'll get the same answer. Yes, Kumar? Yeah. Yes, yeah, so ultimately the math works out in a way that your junction rule is still satisfied. All right, so it will basically be a summation of the fact that the current going in must be equal to the current going out. So here what we have done is that I2 goes in, I3 goes in, and I1 comes out. Actually, in actuality what happens is I2 comes in, I1 and I3 both goes out. That is what that is how the math works out. All right, but yeah. What do you mean numerical? So don't be so sure, because তখন আপনার loop equation গুলোও কিন্তু একটু different হতে পারতো. So it's not as simple as just looking at the last equation, right? Because then you would have loop equations with different signs. Okay. Yeah, so just pick a direction, go with it. Your final answer tells you actually কোন directionটা আপনার opposite ছিল. That is it. Alright, so now the slide's going to get very messy because I've written over them, but it doesn't matter, we move on. Alright, so all of these I worked out for you, so we don't need to go through them. We have the last discussion question to talk about. Take 1 minute to answer this. Thank you. So after this, submit your form and then I will close the responses, then we'll talk about the answers to each of the questions. Yeah, the circuit, in that part of the circuit would now be active. Yeah. So the form is designed in a way that it allows one submission. So you're out of time anyway. No. What you can do is maybe I don't know. I use a different email account. Right. So everyone should have submitted by now. All right. Okay. So take a minute. Last minute. Okay. Fine. Last minute. Yeah. Okay. Okay, fine. Keep submitting. Basically, the lecture is done. We are just going to discuss the answers now. Right, so I think most of you submitted, probably 1 or 2 people left, so finish it up. All right, so everyone done? Okay, I'm closing the responses. All right, closing the responses. Any objections? No. Okay. আপনারটা সাবমিট হয়েছে মাত্র gmail.com. Alright, so closing the responses, good. Okay, so now let's discuss the answers. For the first question, what is the physical quantity represented by the slope? So remember, P equals VI, and this is a straight line through the origin. So then P versus V, what is the remaining quantity? That is I. So then you get the current. Shakawat Hussain, কোন section? 14. আপনারটা সাবমিট হয়েছে, it's fine. Alright, moving on. So this is the current, so the answer is A, Y equals mx. M would be the slope, and M here is current, I. Now for the second discussion question, resistance in a constant voltage circuit is doubled. So constant voltage, what is the power? Well, then you use the power relationship with voltage and resistance. Yes. Oh, okay. So thank you. It's already included, so I will just mark it over. Anyways, so this is V squared over R. You double the resistance, you have the current. I think this was also discussed. So you take one bulb away, it gets the whole potential, and that is answer C. But those were not part of today's discussions, as Atika pointed out. So moving on to discussion 4. So three resistors R1, R2 and R3 are connected in series, which will result if the resistance of R3 is increased. So the circuit was like, basically you have three resistors in series. If you increase one of the resistance, what will really happen? So what will happen to the current, in fact? So V equals IR, so if you increase one of the resistance, R3, then the total resistance goes up. So if the total resistance increases, then the current must decrease. So therefore, the total current in the circuit will decrease. The answer is E. For 5, we have a 100 watt light bulb placed in series with a 60 watt light bulb, given that the brightness is proportional to the power, which will burn brighter. So again, two bulbs connected in series, so they get a share of the EMF. The voltage is different, but the current through them is the same. So since the current is the same, to determine power, I would use this relationship, P equals I square R, because one of the term is constant, I is constant. So if you have bigger resistance, then you produce like more power, right? So therefore, more resistance equals more power. R can be determined by considering the bulbs in normal operating voltage at 240 volts. So you are connecting to the power supply provides a constant voltage of 240 volts, which can be used to find resistance using Ohm's law. I can use power to do that. So power is given 100 watt and 60 watt. So power is V squared over R. V is constant if I plug it in. So then the initial resistance I can easily calculate from this equation. So power is, let's say for 100, it's 100 watt light bulb. Then you have V squared over R. V is 240. So R would be V squared over power. So 240 squared over 100. For the 100 watt bulb, you get 576 ohm resistance. You do the same thing with the 60 watt bulb, you get 960 ohm resistance. So the 60 watt bulb has more resistance, so it dissipates more power. So 60 watt burns brighter. Okay, so the answer is A. So even though it has a smaller power rating, the 60 watt bulb will glow brighter because it has more resistance, and resistance for a constant current circuit, series circuit, resistance is proportional to power. Alright, now you have this combination of resistors. I wanted you to determine the true statement. So it's not very straightforward, but one thing is straightforward is that R1 and R2 is not in series, because basically if you look closely at R1 and R2, the ends of R1 and R2, they're both common to one another, so it's basically parallel. So you can take R1 and place it here, it would exactly look the same. So also you can think about it another way. Let's say the current comes in this way, and then it sees two branches, so the current divides out. So if the current is dividing out, they cannot be in series. So R1 and R2 cannot be in series, alright? So they have to be parallel. Another thing is this circuit, R3, R4 and R5. So again, let's say the current comes through in this direction, let's say, and sees two branches through R3 and R4. So current comes in, goes one way through R3 and another way through R4. So again, the current is dividing out. So R3 and R4 cannot be in series. R4 and R5 must then be in parallel. So the things that are sure is that R1 and R2 are in parallel, R4 and R5 are in parallel, and we cannot really say much for R3 apart from the fact that R3 and R4 cannot be in series because the currents are different. So the only true statement in the options was D. Alright. Now the last one, we have the three bulbs in a circuit, all identical, so all of the same resistance. What happens to the brightness of A when the switch is closed? Before the switch is closed, what is going on? You have two bulbs, A and B. And A and B basically are put together in series before the switch is closed, right? So then A and B shares the EMF and they glow, because they're identical, they glow equally brightly because their resistances are equal. If you close the switch, that means you're activating the later part of the circuit, the second loop. That means now the current has another way to go, not only through A and B, but rather through B and also C. So the current divides out at that A junction, right here. So that means the total current goes through A and then divides out into B and C, but C is connected in parallel. So you're connecting equal resistance in parallel. And what we have seen before, the more resistor you add in parallel, the overall resistance goes down in the circuit. So if the overall resistance is now smaller, then the overall current, the total current must be larger. So the total current is passing through A, so that means the current through A increases because power is proportional to the current, and R is constant because R is same for each of these lamps. Therefore, the brightness goes up. The answer is B. Okay. Alright, so that's it for today's class. Thank you for joining. And yeah, so there will be a homework posted. The submission for this homework would be online, so don't worry about submitting in person. Get started on the homework. The quiz is until this. This is the quiz syllabus. This is where the quiz syllabus ends. Alright, so get started on the homework as soon as possible. That will help you prepare for the quiz. Thank you. Attendance is waived for today.